All right, so we are going to have a look this morning at osmosis. Osmosis obviously has a lot of biological impact. We'll go through a quick introduction and then a little bit more in depth in the notes. So we have to kind of start with the concept of a colligative property. As a review, we've talked about the Van Hoff factor, and the Van Hoff factor really just looks at how solute behaves when it enters solution. So, for example, pictured is sodium and chlorine, and sodium and chlorine in solution will dissociate from sodium chloride to form 1 mole of sodium ions, pictured here in purple, and 1 mole of chloride ions, pictured here in green. Well, the reality is that in a solution that is neutral, like water, although it does have the slightly negative and positive sides, but the net charge on water is neutral. The ions, the anion and cation, shown here, the green and the purple spheres, they could potentially reassociate, and that is what the Van Hoff factor talks about. So if sodium and chloride ions reassociate, then our assumption that 1 mole of sodium chloride produces 1 mole of sodium and 1 mole of chloride exactly, or 2 moles of solute, is actually incorrect. And when we do this, we need to take into account that there are some particularities of a solution that as concentration goes up, for example, we will see the solution behave a little bit differently than we predict. So in the table that's shown here, you can see 4 compounds listed. One is sucrose, which is a sugar. You'll notice that its value, or how many moles of ions it will produce, is 1 across the board. Regardless of the concentration, we have a 0.1 molal, 0.01 molal, 0.001 molal solution, and they all show 1. That's simply because sucrose does not dissociate. The limiting value column on the right tells us the maximum number of moles of solute that could be produced from 1 mole of the dissolving solid. So we look at sodium chloride. We know that sodium chloride will produce 2 moles of solute. That's why its limiting factor is 2. But when we look at the Van Hoff factors, or the concentration at various points, a 0.001 molal solution will only produce 1.97 moles of solute. So when we look at this, we can see that as the concentration comes up, it is more likely that the ions will find each other in solution and reassociate. So when you get to 0.1 molal, the Van Hoff factor, or the number of moles that will be produced, is 1.87. We can see potassium sulfate shown here, where its limiting factor will be 2 moles of potassium and 1 mole of sulfate. Ideally it's 3, but at 0.001 we see that it drops off considerably more than the sodium chloride did. And that is simply because sulfate has a charge of -2. It is more likely to pull together. Magnesium sulfate will normally produce 2 moles of ions, so it has the same limiting value as sodium chloride, but because sulfate and magnesium both share a charge of 2, positive and negative obviously, they are more likely to reassociate. So that takes us to osmosis, and osmosis seems to be something that comes up a lot in biology. The concept behind osmosis can be a little tricky to understand, but the first thing that we need to understand is that you have 2 different solutions, whether it's inside and outside a cell, or simply on opposite sides of a chamber, but those chambers are separated by a semi-permeable membrane, and that will allow small particles to pass through, but the semi-permeable membrane will block the larger particles. In osmosis, what we're talking about is the movement of water, but the solute itself is not able to move. So we look at this three panel diagram, and we can see on the left-hand side, we have a concentrated solution on the left and a dilute solution on the right. So when concentration is unequal, water will want to move. They'll want to fix the problem. So you can't really think of the concentration of the solution as it with respect to solute here, because water is the solvent. Water will want to move in the direction where the solvent is higher to where it's lower. So it's going to move from the dilute solution, the water, to the concentrated solution. So effectively diluting the concentrated solution. When this happens, if you have water moving from the right to the left, the amount of water, or where this column is, will start to drop. This drop is referred to as osmotic pressure. It will get to a point where the pressure difference is so great that osmosis will stop. We can force this back if we want, but it will require pressure and work. Now, in chemistry, we can actually measure this, and we represent it by capital letter pi, and we'll notice that this equation very much represents or resembles the ideal gas equation. So focusing on the part on the left, it says that pi is equal to I n over v RT. And the reason I is there is because this is a colligative property. That means that the type of solute doesn't matter, it's just the number of particles free in solution. On the right, we have, instead of n over v, which is basically molarity, so it is molarity, we can represent that with capital M. R is the ideal gas constant, and T is the absolute temperature, so in Kelvin. I has no units. So we can come up with this idea that there should be a solution, there should be a system that we create where the osmotic pressure is 0, or in other words the same on both sides, the difference, in which case we have an isotonic solution. This has a huge application in blood cells, because if a solute concentration outside the cell, so it's more salty outside the cell than inside, we say that the concentration outside the cell is greater than the inside, therefore it is hypertonic. What will happen is, because there's high solute present outside the cell, is that the water inside the cell will leave the cell to try and dilute that solution. This will lead to a situation called crenation, and basically that is the shriveling up of cells. The opposite, of course, can take place. We know that red blood cells are kind of donut shaped, without, of course, the hole. If the concentration outside the cell is very low, and meaning, in other words, the cell is saltier than its surroundings, if I put a cell in fresh water, for example, what will happen is the water from the outside the cell will want to enter the cell, and this will cause the cell to swell, and this will create a condition called hemolysis. So as we move into this concept of osmosis, we switch over to our handout, a lot of what we just talked about within the PowerPoint is the same, but there's a couple things we just want to make sure that we are clear with. So first things first, the membrane needs to be semi-permeable, just as a review. We are talking about the movement of water molecules. So there is this understanding that solutions will move from the more concentrated to less concentrated side. And osmosis, we're not talking about the particles, we're talking about the water molecules themselves. So in this case, we are only talking about the solvent molecule. That is osmosis, the movement of water from an area of high solvent concentration to an area of low solvent concentration. The goal of which is to attain equal concentrations. And the blurb that's here, you can go through and read. but it's basically a summary of what I've discussed already. So we have this diagram that was shown within the PowerPoint, and there are three parts to it. So there's an initial, an equilibrium, and of course a restoration. So looking at the first one, the initial side, is we have one side that is pure solvent, and then we have a solution. So clearly this side is more dilute than this side. This side has no solute, and this side has solute, so it's obviously more dilute. The semi-permeable membrane exists here. So there's a lot of water molecules here in a given number, and there's not as many water molecules per given number on this side. So naturally, water wants to move across that membrane to even out the number of water molecules per given molecule. If this process continues to take place, the amount of liquid, or the amount of solvent in this case, will drop, forcing the right-hand side to be even higher. Because at equilibrium, we'll get to a point where water molecules will start to bounce back and forth at equal rates. The difference here, and again, we can see our start level, and we can see how much we've dropped from our start level. The difference here is how much pressure do I have to apply to this side using something like a piston to push this back down. That is called osmotic pressure. So osmotic pressure is represented by capital pi normally rather than little pi, because otherwise it gets confusing, but you will see pi represented. And you have to be very much in tune with what you're doing to understand what pi is being used for in that particular instance. So let's look at this equation. It says the osmotic pressure, pi, is equal to the Van Hoff factor, N over V RT. Or, because N over V is molarity, we could just write I M RT. The equation is very, very similar to the ideal gas one, as we've already said, but it's actually a pretty easy question to use. The Van Hoff factor we will assume is ideal. So for example, we would assume that for I, if we were dealing with sodium chloride, we would use I equals 2. So we'll assume the ideal unless we are told to do otherwise. So we're going to get back to this blood issue. And we'll talk about a couple different situations that we know of in biology and chemistry where this becomes pretty important. So we have some vocabulary building to deal with here. First of all, if the concentration of solute is the same across the semi-permeable membrane, we say that the solutions are isotonic with respect to each other, or the same concentration. If one solution is of lower osmotic pressure, it is considered to be hypotonic with respect to the more concentrated solution. So the more dilute solution compared to a concentrated solution is hypotonic. If we look at it the reverse way and we look at the concentrated solution with respect to the dilute one, we say that the concentrated solution is hypertonic with respect to the dilute. So in the PowerPoint we talked about crenation, which is this, and hemolysis, which is this. It is very important that the concentration of solute outside your body, outside your cells or in your intracellular space is constant. Otherwise, your cells can do this, and this will obviously create health problems. So I've come along here and I've defined crenation and hemolysis as I already have, but once again, crenation is the shriveling up of a cell where the concentration of the solution outside the cell is higher than inside, or in other words, the outside is hypertonic compared to the inside of the cell. So this will cause movement of water out of the cell into the more concentrated outside. So we end up, basically the water in the cell wants to help dilute the solution around it. Hemolysis is the opposite in pretty much every way. The cells will rupture at this case. If you need to read more about this or you want a couple more concrete examples, it is on page 554 of your textbook. So we're going to do a couple worked examples here together to see how this actually applies. And I'm trying to make them as realistic as possible, but there will be some liberties that we will take into consideration. So first of all, the first example says the average osmotic pressure of blood is 7.7 atmospheres at 25 degrees Celsius. What molarity of glucose will be isotonic with blood? In other words, if we're injecting somebody with glucose drip, what concentration should it be so we don't mess up that the osmotic pressure of the cell? In other words, we want it to be isotonic. So we know that we have an equation that says pi equals Van Hoff factor times molarity times the ideal gas constant times T. I have the osmotic pressure. I have the Van Hoff factor because it's glucose, so we're assuming I is equal to 1. I am looking for molarity. I obviously have the gas constant and I have the temperature. I can't deal with 295. I've got to deal with absolute, so it's got to be 298 Kelvin. But I have everything except for molarity. So I will solve M is equal to pi over IRT. So the biggest, I guess, trick here is making sure that you understand whether the solute is an electrolyte or not. In this case, we assume glucose is not an electrolyte or a non-electrolyte. So 7.7 atmospheres divided by 1 for the Van Hoff, 0.08206 liters atmospheres, moles Kelvin, and 298 K. So atmospheres cancel, Kelvins cancel, liters will be on the bottom and moles will be on the top, which is what we want. The molarity will be 0.3149 moles per liter, C6H12O6. So a solution of 0.3149 moles per liter of glucose will be isotonic with respect to our blood. Obviously, blood's not going to be at 25 degrees Celsius, at least hopefully not. It'll be closer to 37 degrees Celsius, which we know is physiological temperature. But again, the process will be the same, just the osmotic pressure might be different at that temperature. We'll just go with what we have in the problem. It gets kind of neat, though, because if we change this question to be NaCl, for example, NaCl will dissociate. So again, we know that we put people on bags of saline in the hospital. Well, saline is basically salt water. And we know that sodium chloride will break into 1 mole of sodium and 1 mole of chloride. In other words, the I for this is equal to 2. So basically, it would be the exact same calculation, but we would put a 2 instead of the 1, and we would get the molarity of, and I'm just going to write NaCl just so we don't confuse it, would be exactly half of that. So 0.3149 divided by 2 is 0.15745 moles per liter. So if we were preparing an isotonic solution of sodium chloride to administer, it would have to be half the concentration of glucose, because sodium chloride is a strong electrolyte, whereas glucose is a non-electrolyte. So we get that difference. Another thing to take into consideration here is that very infrequently in health science would we deal with molarity. A lot of time they'll deal with percent mass. Once again, I'm not a nurse, but converting to percent mass is sometimes something that could be useful to do. So for example, if we were dealing with, let's write this in black, let's convert this to, I want to convert this to percent mass NaCl. Again, not part of the question, but just something that we should practice with regards to solutions. So I want to know what percent mass of NaCl I should be administering to create an isotonic solution. So it would be different for glucose simply because glucose is going to have a different concentration. But we can do a couple things. 1,5,7,4,5 moles per liter. So what I'm doing in black is not really part of the problem. We're just doing that conversion to show that how we do it. So that's the concentration I would need to be isotonic. So 58.44 grams for 1 mole NaCl go along and do this. 0.15745 times 58.44 equals 9.20 grams per liter NaCl. So I've dissolved 9.20 grams of sodium chloride in every liter of solution. We'll make a couple assumptions here. We'll make sure that we'll assume that the bag is at 20 or 25 degrees. So to get percent mass, it's the mass of NaCl over the total mass of the solution times 100. Well, we can turn to Appendix B in your booklets or in your textbook, and we can find that the density of water is about 0.997 at 25 degrees Celsius. So let's turn this liters. Let's turn this liters into a mass. So if we have 1,000 milliliters of water, and we have 0.997 grams per mil at 20 degrees, we're going to get 997 grams of H2O. And again, it depends on the temperature, and I'm just trying to take us through looking at different aspects of solutions. So I'm going to have to jam it in here, but 1 liter of solution is going to have 9.20 grams. 9.2 plus 997 times 100. Again, really kind of cramped in here. 9.2 divided by 9.2 plus 997 equals 0.91%. So an isotonic solution of sodium chloride with regards to a blood cell would be about 0.91% mass for this. So that is what it is. It's called kind of a physiological dose or a physiological isotonic solution, which is again just a neat application of what we are trying to do and what we're working with. So let's go down and have a look at the second example question. It says the osmotic pressure of an aqueous solution of a certain protein was measured to determine the protein's molar mass. The solution contained 3.50 milligrams of protein dissolved in sufficient solution to produce 5 milliliters of that solution. So we measured the osmotic pressure and found it to be 1.54 torr. So right away, I'm identifying a couple things that we're in torr, which is not the right unit. We're in degrees Celsius, which is not the right unit. And we're in milligrams, and we're going to have to deal with that later. So a little bit of biology knowledge comes across is that I know that proteins have huge molar masses. They are very big molecules that can have thousands of atoms in them. So we're expecting a pretty big answer here with regards to what we normally see for molar mass. But we start with the same basic question. IMRT. So I have osmotic pressure. I have I, because we're treating it as a non-electrolyte. I have R, I have T. I have a couple things to sort out. First of all, pi is equal to 1.54 torr. So that's times 1 atmosphere over 760 torr. So that would be 2.026 times 10 to the negative 3 atmospheres. And temperature is 25 degrees Celsius. So that's 298 Kelvin. So I think we're good to go. The only thing we don't have is we do not have the molarity. So let's rearrange. Molarity is equal to osmotic pressure divided by IRT equals 2.026 times 10 to the negative 3 atmospheres. It's a non-electrolyte, so that means it's a 1 for I. 0.08206 liters atmospheres mole Kelvin, and the temperature is 298 Kelvin. So that means that the molarity is 8.286 times 10 to the negative 5 moles per liter. So I know the number of moles in 1 liter of solution, but I only had 5 mils. So I know that the number of moles is going to be equal to molarity times volume. So 8.286 times 10 to the negative 5 moles per liter times 0.005 liters. So that gives me 4.143 times 10 to the negative 7 moles of the protein. Finally, I know that molar mass is equal to the mass of whatever you're dealing with divided by the number of moles. So I know I have 0.00350 grams, and that's just from up here in the question. And now I have the number of moles. So 8,450 grams per mole, which is pretty much what you would expect when you're looking at a protein. Otherwise, if you're not really familiar with proteins, you might think that that answer is wrong just because it is so large. So now we're going to do a couple try this problems. And what I would recommend that you do is, if you have the handout or if you printed out the handout, would be to sort of pause here and try and apply what you've learned so far to these 3 questions. And when you are done, then hit play again and see how you did, or at least go over it and find out what you don't know or what you need to sort of improve on here. But first of all, let's go through the try this then. Seawater contains 34 grams of salts for every liter of solution. Assuming the solute consists entirely of NaCl, which again is about 90% of what's in our ocean, calculate the osmotic pressure for seawater at 20 degrees Celsius. So I need molarity. So 3.54 0.4 grams NaCl in 1 liter times 1 mole of NaCl is 58.44 grams, I believe. So 0.5818 moles per liter. Now, we could write out the dissociation equation for NaCl again. NaCl solid will dissociate into 1 mole of sodium and 1 mole of chloride. That means that if you were to look at the Van Hoff factor, 1 mole ideally would produce 2 moles of solute. So we write pi is equal to I mRT. Pi is equal to 2, 0.5818 mole per liter, 0.08206 liters atmosphere, mole Kelvin. And you gotta watch it, it's 20, not 25. So it's 293 Kelvin. Pi is therefore 27.99 atmospheres. I only have 2 significant digits, so pi is equal to 28 atmospheres. It would be the osmotic pressure of seawater. Question 2 is a very good question with respect to solutions and colligative properties altogether, for a couple of reasons. One, because it's going to sort of get that Van Hoff factor applied, so you can start to see how we can use it. And first of all, we're dealing with calcium chloride now. So I know that when calcium chloride dissociates to strong electrolyte, aqueous, it's going to produce, ideally, I equal 3. But again, that is the ideal, or the limit. This question is asking me to find I for this solution, and I've left a lot of space for you, so probably that's not the easiest way to do it, or it's not the easiest way. It's not the correct way to do it. So we're going to have to check. We're going to go through this process. So let's just quickly take stock of what we have. So first of all, I see the osmotic pressure listed, 0.674 atmospheres. I see molarity at 0.010 moles per liter. I see T is equal to 298 Kelvin, or 25 degrees Celsius. So I know that I can go through and check it. Pi equals I mRT. I can go through and check to make sure that I is equal to 3, if that is the easy way that we're going to do it. Now, the one thing I know by writing out that equation is that I cannot exceed 3. So if I get an I over 3, I've done something wrong, or there's a significant problem with the question. So we're going to solve for I. So I is equal to the osmotic pressure divided by the molarity, the ideal gas constant, and temperature. So I is equal to 0.674 atmospheres divided by molarity, so just check to see what units we have left. Atmosphere is going to cancel. Moles and liters are going to cancel, and Kelvin's going to cancel. All of my units are gone, so that means I probably have I set up correctly. And when I solve for I get 2.75 unitless. So the Van Hoff factor is 2.75 here, which is less than our limit, so that's okay. But that just tells me that some of these calcium and chlorides are starting to reassociate. finally, question B says, how would you expect the value of I to change as the solution becomes more concentrated? Explain yourself. So we've talked about it within the PowerPoint to start of this lesson, but as the concentration goes up, it is more likely that the solute particles are going to reassociate, especially when they're charged, because they're going to be attracted to each other. So I will expect I to decrease or become smaller than 2.75 because ions will more likely recombine. And that's basically the last colligative property that we need to talk about, which was osmotic pressure. But more importantly, it's nice to sort of round off and use the different types of concentration that we can talk about, and then the problem solving and understanding exactly what solutions are doing based on concentration, Van Hoff factors, all that kind of stuff. So it really does seem to kind of round up nicely with osmotic pressure.